This talk is going to be about some quite well-established science and also very speculative ideas that I can talk about because I'm no longer paid to be a particle physicist, so I can say things that might get me not a job if I was a student or something like that. So, okay, I've got to use this, right? I've got to use this. There we go. So, this is the history of the universe in 3 short verses. It's a poem I wrote that is in my book, Shameless Promotion, Space Times Matter. I've got a few copies out there if you want. 100 short stories about the universe, stories being non-fiction, flash non-fiction if you like, short things. So I'm going to read this poem because it's got an essence in here. In the beginning was the Word. Was the Word, oh, I can do it here, so, no, In the beginning was the Word. Was the word bang? Not big, but teeny tiny, 1,000 billion stars inside a grain of sand. Even smaller than an atom. They would emerge after 1 billion years with circling planets and later life. Is that how it all began? Now is the time of our lives. It took 13 billion years, but here we are. 100 billion interconnected neurons in your brain. The plan encoded, DNA in every cell. Ultimate complexity, asking questions, seeking answers. Is that why it all began? But in the end, all life will die. When the last star burns out, extinction everywhere. The part is over. Dark energy blows the universe apart. Is consciousness no more, or is it everywhere? Big bang, then life, then empty end. Is consciousness no more, or is it everywhere? So, this one's got to use. So here, a story about my path to Unitarianism. I was brought up in England, and we went to Church of England, church brought up like that. And then when I was later studying physics at school, decided I didn't believe in some of the miracles we were told to believe in. I couldn't believe that Jesus actually walked on water or went bodily into heaven. So I stopped going to church for many decades, actually, until somebody told me about the Unitarian Church. I was living in Naperville near Chicago, and that suited me just fine. So, miracles, and gods. So, the ancients believed in gods as things that they were very powerful things that they couldn't understand, like the sun, the moon, lightning, powerful and sometimes scary things they couldn't understand, so they worshipped these gods. When I joined the Unitarian Church, I went to a course called Build Your Own Theology, and we were encouraged to think about what we thought about God and the universe. And I decided that there are 3 things that we don't understand by modern science, and they're the universe as a whole, there's life as a whole, consciousness, and part of consciousness is, of course, in love. So that's for a while my trinity: universe, life, and consciousness. And of course, this one, miracles. Well, what do I mean by miracles? 2 dictionary definitions of miracles. One is an extraordinary and welcome event that is not explicable by natural or scientific laws and is therefore attributed to a divine agency. So the last bit I put in red because I have a question mark about that. What do you mean by divine agency? But the first part is clearly a good definition of a miracle in my terms. Another is a remarkable event or development that brings very welcome consequences. And you can think that the beginning of the universe was a remarkable and welcome event that we don't understand, but brings obviously welcome consequences. Here we are. So what I mean by miracle is something amazing that, while not violating established laws of physics, didn't have to be true, but is true, and allows us to be here as living, conscious beings. I don't include things like walking on water and turning water into wine that put me off my Christian faith as a child, but I do include masses of and forces between particles, life, and the beginning of the universe. So these are things that we don't understand. The question is whether anything, how these can be brought as religion together with science. So about the composition of the universe, we know so little about it, really. We study particles and the forces between them. That's what I've been doing for about 60 years. But these make up matter, atoms and stars and gas and dust and so on. It's only about 5% of the stuff in the universe. There's about 5 times more stuff called dark matter. We don't know what it is. Most physicists think it's made of particles we haven't yet discovered, either because they're too massive to produce even at the Large Hadron Collider, where I work, or it's so weakly interacting that they haven't been produced, they're so difficult to detect. But I'm working on a project to look for these things. Now, the matter we know about, the atoms, is on the right there's a table, a fundamental table of particles that we know, and there are 6 particles called quarks. The U and D is called up and down. They're just names. They have a reason for that. And the electron, and I've circled those because all atoms are made basically of protons, neutrons, electrons. Protons and neutrons are made of up quarks and down quarks. And the others, the C for charm, S for strange, T for top, B for beauty, are very unstable. They decay almost immediately after they're produced. The top and bottom were discovered at Fermilab, where I work. I happen to be part of the top team's discovery. And then the electron, which is circling in our atoms, it has a little mass, it's only about 1/2000th the mass of an atom of hydrogen, but then it has heavier partners called the muon and the tau. And then the electron also has a partner with no electric charge and very little mass. It's called a neutrino. And these 3 other particles, electron, muon, and tau, have neutrinos going with them. That's a mysterious thing. And then the forces between these particles are carried by other particles. There's a Z boson, a W boson. They were discovered at CERN. The gamma is a particle of light, electromagnetic waves. And G stands for gluon, which is a particle that binds together quarks, like up and down quarks, inside protons and neutrons. And so I'm going to talk about some of the miracles that I consider amazing, actually remarkable things. One is that neutrons decay and protons don't decay. Now, neutrons and protons are almost the same particle. They're made of quarks, basically a deeper level. I see on the left, D, U, and D. That's 2 down quarks and 1 up quark. That makes a neutron. The proton is 2 up quarks and a down quark. So the difference between them is one's got a down quark and turns into an up quark. And the mass, there you see the masses of these particles. The neutron mass is 939, in some units, 939.565. The proton is a little bit lighter. The difference is only 0.14%. Now, why is it heavier? Why is the neutron heavier than the proton? Only just enough for it to decay away in a life of about 15 minutes. So after 15 minutes, half of the neutrons are decayed away, and half the less. So if it was the other way around, if the down quark was a bit lighter than the up quark, so that the proton was a bit lighter than the neutron, then all the protons would have decayed away, and there'd be no hydrogen, because hydrogen is made of protons and electrons. Now, we don't know why the down quark is a little bit heavier than the up quark, but it allows life and us to exist. And I consider this something quite amazing, because as far as the physics we know, it could easily be in the other way around, and in some different universes it would maybe well be the other way around, and there'd be no hydrogen and therefore no life. There's another miracle which is about carbon. We're made of carbon. It's the only element among 100 or so elements that allows very complex molecules to form. And Fred Hoyle, who was a great science fiction writer, actually, but also a cosmologist, didn't understand how there could be so much carbon in the universe, because the Big Bang produced only hydrogen and helium, a little bit of lithium, the first 3 elements of the periodic table. So after the Big Bang, stars started to get formed by condensing gas clouds of hydrogen and helium. And to make carbon, you have to get 3 helium nuclei to stick together, which obviously is rather difficult, because when 2 stick together, they make beryllium, which has 4 protons and 4 neutrons. But that beryllium has to be stuck together with another helium nucleus to make carbon. But the problem is that beryllium is very unstable. It decays, falls apart with a half-life of about 8 times 10 to the minus 17 seconds. Very, very short time. That's 0.16 zeros and then 1 second. And so he said, in order to produce enough carbon, there has to be a special state of carbon where the nucleus is excited by protons and neutrons taking internal kinetic energy. And the energy of that excitation state, he calculated, has to be between about 7.3 MeV, that's a million electron volts, just a unit of energy, and 7.9, between 7.3 and 7.9. And Fred Hoyle, who was in England, told a physicist at Caltech, Fowler, look for that state in the carbon nucleus, and he found it at 7.656 MeV. And that is a balance between repulsion and attraction. I say that because the carbon nucleus, it's got 6 protons in, and they're mutually repulsive because they've all got positive charge, and they would fly apart. But it's stuck together with neutrons, and it's struck together by the strong force of attraction. So we've got a balance, a careful balance between the strong force of attraction between the protons and neutrons and the electric charge which is trying to blow it apart. And that's a careful balance that gives this internal excitation energy of 7.6 MeV, just where it was expected to be. It's interesting that allows carbon to exist in the amounts that enough to make life. I got to say something about the Higgs boson, because the Higgs is a field fills the universe. Now you know about gravitational field that holds us down on the Earth, and electromagnetic fields, and so on. These all have directions and different magnitudes. But there's another field predicted to fill the universe, and that gives particles their mass. Like if they're trying to plow through this field, they pick up mass. And that's how the up and down quarks get slightly different masses. So Higgs and he predicted in 1964, just the year I started doing research for my PhD, that there should be a particle, a quantum of the excitation of this field. And the field has no direction, just a value everywhere, uniform through space. In 2012, we found the Higgs boson at CERN, and there are 2 big experiments. This is the one I'm working on, actually. You see how big it is with that person down there. It's massive. And we discovered the Higgs that way in 2012. One way was decaying into 2 gamma rays that actually I'd discussed 23 years ahead of time. So that was very exciting for that. Now, let's go out and look out into the universe, into the sky. Now, many of you have probably seen images from the James Webb Space Telescope. There's a picture of it on the right there. It's an amazing technical achievement that they got this thing up in space with all those mirror segments, and they've got them together to make one beautiful, smooth mirror. And there you see an image, which was a 12.5-hour exposure. There's a cluster, and that is about the size of a grain of sand or a pinhead at arm's length, staring at that. And in this picture, there are only 3 stars. You see the top and the bottom, there's little stars with 6 points. The 6 points, an effect of the mirror, which has a diagonal, hexagonal symmetry. So all the other things in that image are actually galaxies, distant galaxies, and they're so far away. The light's been coming from them for about 10 billion years or so. And an interesting thing also in that picture is that you see some of the galaxies are distorted into arcs, and that distortion is actually from a galaxy in front, a cluster of galaxies that's bending the light from galaxies much further behind. So the background making arcs from galaxies about 9.5 billion light years away. But most of the image is dark between the galaxies, you see. And the dark is rather important, actually. Because if the universe was infinite and static, so stars in all directions forever and ever, amen, then the whole sky would be as bright as the surface of the sun. So the surface of the sun, if you take the sun 2 times farther away, it gets 4 times smaller, but the surface brightness is also 4 times, is the same, the surface brightness. So if every direction you look, if the universe was infinite and static, your line of sight would hit the surface of a star, and the whole sky would be as bright. It's not as dark. So this was realized a long time ago. Olbers is named after Olbers, who called it a paradox. It's not really a paradox, but you can conclude from the fact that the sky is dark in between those distant galaxies that the universe is either not static or not infinite or both. I think it's neither static nor infinite. We discovered it's not static. We discovered it's expanding. So, what you're looking at in the dark there is called dark energy, actually. So why the sky is dark? Einstein actually said maybe space is not infinite, but he thought it was still everlasting from infinite past to infinite future. I don't know why he thought that actually, but he was surprised when Hubble discovered the universe is actually expanding, and that was, he then said, oh, I could have predicted that from his theory. In a nutshell, Einstein in 1905 had some amazing papers. It's a miracle year, if you like. One thing was special relativity. Light travels at a speed of about 300,000 kilometers a second in a vacuum in all directions. It doesn't matter where you look. Now we're moving through the universe. We're moving around the solar system, around the sun. We're moving around the galaxy. So we seem to be moving through space. So if light was a wave in a medium, like a wave in water, it should have a different speed depending on which direction you're going. But it's not. And that was demonstrated. And he said, he was thinking, how could I overtake a light beam? Could I catch up with one and overtake it? What would happen? Would light go backwards or stop or what? And he decided that suppose we can't do that. Suppose that the speed of light is the same in all directions. And he came to the theory of special relativity where space and time are merged into a 4-dimensional space-time, and they get mixed up. So space and time are different for people traveling in different speeds. So if I run around here, it's different from me, but you have to get close to the speed of light to make a really big difference. But we've certainly demonstrated that in many ways. Clocks run slower when they're going fast with respect to you, and so on. They appear to. Now, the other thing, the next big step was general relativity, where he said you cannot tell how fast you move if your speed is constant. So you can be in an airplane and you can drop something on the floor. You can't see that the plane is moving at constant speed. It just falls down. Of course, from somebody outside, they'll see the thing you dropped going forward and so on. But then he had a major realization that actually accelerating and gravitation are linked. In fact, the same thing. If you're accelerating in a car, you feel it pushing in the back seat to the back seat. You're accelerating, it's a force, rather like the force of gravity. So, and planets in orbit, they seem to go in a circle in space, but if you stretch it out in space and time, they go in a spiral. They're going actually as straight as they can in space-time. Anyway, that leads to general relativity, space-time being not flat, but actually bent by mass. Now, that is leading us to, and led Einstein to the idea that space is bent by matter, the whole universe is full of mass, so 3-dimensional space should be bent, the universe closed and finite. Now, I brought a show and tell here because this idea that space could be closed and finite is hard to grasp, but I couldn't resist buying this for a few dollars, actually, whatever it was, because it's a beautiful sphere, right? Now, that sphere, the surface is finite, right? It's got no edge, and it's finite. You can go off in any direction you like, and you'll eventually get around the whole sphere and come back where you started, like on Earth. You go off in a direction as straight as you can, but staying on the surface of the Earth, you'll come back where you started. You've got all around the surface of the Earth. Now, Einstein had the idea that maybe three-dimensional space is like that. That's a two-dimensional surface. And by the way, if it's the Earth and you look just around you, it looks flat. If you just look, a small area around you, it seems flat. And this, for a tiny ant on this sphere, it would look flat. But actually, if you got further and further away, it begins to see curved. And one nice picture about how the surface of the Earth could be finite is you imagine that you start off with, say, with wrapping around you a tape over the Earth, and you get bigger and bigger and bigger and bigger. It gets straighter and straighter and straighter, and then it starts getting smaller and smaller and smaller as you've gone past the equator, and eventually you get down to the South Pole, and you've covered the whole Earth with tape. But when you get to the South Pole, you find you're inside that. Anyway, it's a hard thing to get around your head, but also there's another little example, which is one-dimensional, so closed one-dimensional. So it's just a loop. It's just a loop here. Okay. Now, this actually is not one-dimensional because it's got width and breadth and so on, so it's actually three-dimensional. But imagine that mathematically you can think of a line as having only one-dimensional, no width, just around the closed loop. So Einstein said maybe the universe is three-dimensional space, but closed with no boundaries. So the universe is not infinite. Now, the fact that it looks pretty flat to us, and astronomers look out into the microwave background, they look out into the farthest we can in the sky, and it looks pretty flat. It's flat to, but they can't say it's exactly flat. It's flat to about 1%. And if the universe is a closed three space like that, it can't be absolutely flat because that would be an infinite surface, infinite. And my idea of cosmology is that nothing is infinite in the physical world. Infinite is mathematics. Mathematics has an infinite number of different infinities, actually. But if I say infinity is nothing in the physical world is infinite, we can't do a measurement. Physics is about measurements. We can't measure anything and get the result infinity. And if infinity is forbidden by hypothesis, it leads to all sorts of interesting conclusions about the universe. One of which is that no singularities if there are no infinities. A singularity, at the end of a black hole evaporation or something, they say it will get to a singularity. I don't believe that, because singularity is a point of zero size and infinite density. And I forbid infinity, therefore forbid singularity. So that's a sort of radical thing. Now, but okay. So now, when Einstein applied his general relativity to the whole universe, the equation said it should be contracting or expanding, because being static was like a pencil balanced on its point. It's unstable. It should be either expanding or contracting. And he thought it was stable. He thought the universe was about the same for the infinite past and infinite future. But then Hubble discovered that the universe is actually expanding, and the nebulae are actually other galaxies, and they're flying apart. The further away they are, the faster they're going. And Einstein said, that was his greatest blunder. He could have predicted that. But what he did, actually, he'd added a term to his equations to make it stable. He thought it was neither expanding nor contracting. He added this term called a cosmological constant. And it's a number in equations, but what does it mean physically? And I come to that. So there's a diagram at the bottom talking about the accelerated expansion of the universe. You see time is going up. At the bottom you have the very beginning of the universe, a Big Bang. Actually, inflation is starting before the Big Bang. The Big Bang, the universe started much smaller than this sphere, actually, much smaller than a proton. And it expanded exponentially, doubling and doubling and doubling And that is attributed to what's called dark energy, which I showed you is about 70% of the universe. Dark energy, I call it really invisible energy, because it's not dark like this is dark, it's actually invisible. So why not call it invisible energy? And that's the term I will use. And the energy in this invisible or dark energy, the value is a tiny number, it's 6 × 10⁻⁻10 joules per cubic meter. To translate that, if you have a cubic kilometer, take a cubic mile if you want, then there's enough dark energy in there to light an 80-watt bulb for about a minute. So it's a very weak field. So now this is, again, the whole universe from small to big. So down at the bottom here is we have life, okay, the scale of a centimeter, a meter, that's our sort of scale. As you go around this Ouroboros, which is actually a very ancient sort of religious thing of the snake biting its tail, if we go up to the left, every tick mark there is a factor of 10 to the 5, which is 10 to the 5, yeah, 100,000 million. And you go towards the left, smaller and smaller, 10 to the -6 centimeters, 10 to the -10 centimeters, you get the atoms. The W and Z bosons are smaller. We don't know about dark matter, where it's there or what scale it is, but there's something there. And then going around the anti-clockwise from us to bigger and bigger, you get 10 to the 5 centimeters. That's a kilometer, mountains. And you go around to the solar system, the Earth solar system. Every tick mark is a factor of 100,000, and you get up to the size of the universe. And somehow this is the whole universe actually started out smaller than an atom, so it's a closed loop in a way. The universe started out, I believe, with a state of perfect simplicity, and complexity evolved. Time is coming around this way as well. Complexity evolved, and now we're about the most complex things we know in the universe. And then it will eventually, in the far future, go back to a state of simplicity, we believe. This time scale I put on the bottom here, a time scale in logarithmic scale, think logarithmically, 10 to the 88 ticks along here, each tick being a factor of 10. The very far left, 10 to the -44 seconds, is called the Planck time, and we believe that could be the time at which the beginning of the universe. Up there you see, actually we know these times very precisely, because the Planck time is 5.391247 times 10 to the -44 seconds. The 60 means the uncertainty in the last two digits. And the time is the time it takes light to go a Planck distance or Planck length, which is 1.616 and so on, 10 to the -35 centimeters. Now, those numbers, those times and spaces can be calculated from 3 very fundamental constants. C is the speed of light, which relates space and time. H bar is Planck's constant that relates energy and time, or space and momentum. And G is a gravitational constant of Newton that relates mass or mass energy with space-time. So at the very beginning of the universe, about 10 to the -44 seconds, it started, I believe, in a state of perfect symmetry. Neither matter nor antimatter. They came in when symmetries started to get broken, giving rise to the masses of these particles. The up and down quark, different masses came from symmetry breaking. And it's evolved into complexity, which is where we are. In the far future, at about 10 to the +44 seconds, or much longer than that, protons will have all decayed away to electrons and positrons and photons, and then eventually, in much further times, all black holes will evaporate away, and the universe will become very simple again. Symmetry will be restored. So the brain, the most complex thing in the universe as far as we know, there's roughly 300 billion interconnected neurons in your brain, okay. That's 3 times 10 to the 11, which is 3 with 11 zeros after it. That's also, interestingly, I think, about the number of stars in a galaxy like our Milky Way. It's also about the number of galaxies in the visible universe. These big numbers, but is it just a complete coincidence that these numbers are similar? Probably it is, but I picture the brain. Are you conscious? I mean, it's just art, right? Are you conscious? What does consciousness mean? It's not something we understand, or I think ever will understand, really, in physics by measuring particles and galaxies and so on. We study the smallest things and the biggest things in physics, but we don't have a physical theory of consciousness, and maybe we never will. Now, these interconnected neurons, I say there's about 100,000 million or 100 billion. They're alive, but they cannot presumably comprehend our consciousness. So they're alive, but not able to understand consciousness or even conceive of it. That's an emergent phenomenon. You don't get consciousness from understanding how the quarks in a proton or how protons and atoms are put together. It's a different scale. You go up in scale from molecules to water, and you get emergent phenomena. So could there be a higher emergent phenomenon where the whole galaxy is connected, even the universe is connected? How could that be possible if we're all limited to the speed of light connecting between life forms in our galaxy, for example? So here's how proteins, there's a DNA structure on the right there, it's a very long chain molecule made of actually just these 5 elements: hydrogen, carbon, nitrogen, oxygen, with some phosphorus. This is apparently the basis of all life, because carbon is especially the only molecule able to make such complex things. Silicon doesn't come close to it. Is there a question? No. Okay. So if you could make a scale of complexity, which is not established, but on the very simplest side, you have a 0, which is electrons, positrons, and photons. They're very simple particles, not made of anything simpler. And that's where the universe started out with these particles, quarks as well. But on the right-hand side, the most complex things, most complex molecules like life. Maybe there's something more complex, but this is our scale. So coming back to this dark energy, and I call it invisible energy, it's some a field filling the universe. Now what we know, established of course, and you probably will know, we have the electromagnetic field, which has particles called photons, particles of light and waves at the same time, weak field and strong field of gluons. These all vary with space and time. They couple to simple individual particles like electrons and quarks. And then radio waves, long waves, made of very vast numbers of very low energy photons. They're not individually detectable, but so we think of them only as waves. Now the Higgs field, which I mentioned before, again has no direction, it's the same everywhere. It's got particles called Higgs bosons that we discovered, and they're very unstable in decay. But now I get into speculation. If invisible energy, which is like a field that fills the universe, not just a number in Einstein's equation, has associated particles, they're like mutually repulsive and blowing the universe apart. They're responsible for the universe expansion, or accelerated expansion. So if it has particles, what would they be like? What properties would they have? Well, theoretically, it's been known for a long time that actually particles called tachyons could exist. They're not forbidden by relativity if they have very low mass, faster than light, and always superluminal. So in principle, if tachyonic fields exist, they could connect the galaxy like a World Wide Web, the galaxy-wide web, a network, because tachyons always travel faster than the speed of light. If you give them more energy, they slow down, come down towards the speed of light from above. If you get less and less energy, they get faster and faster. And eventually, if you had close to 0 energy, they'd have close to infinite speed. Now, a far-out idea, and this is certainly not established by anybody, but maybe tachyons don't couple to individual particles, like radio waves don't couple to individual electrons, but to complexity, to life, to neurons. So this is where I'm thinking about moving towards life being connected to this invisible energy. Not the invisible energy that I told you about that's so very weak that's blowing the universe apart, but another another type of tachyon in the same properties, but a different mass, if you like. So here's a picture of the Andromeda Nebulae. We used to think it was the whole universe. When my dad was born in 1897, and at that time, people thought the Milky Way was it. That was all it. About 100,000 million stars in that galaxy, and we think most of them have planets now. So maybe if 1 in 1,000 have some form of life, that's still 100 million with life, but perhaps only one is us, has actually life so complex that it becomes conscious and has meaning, if you like. Last night I was at a talk by a friend of mine called Brian Cox in DC. He does an amazing talk with terrific videos, and he talked at the end about how it's conceivable that in this galaxy, although life may be abundant at some form, like single-celled life, which existed for billions of years before it decided to join forces with other cells and make the beginning of evolution to us, that it's possible that we're the only one in the galaxy that has meaning. Now, it takes light about 100,000 years to go across the galaxy, but if there is this tachyonic field that couples to complexity, it could cross in seconds. And is this part of Unitarians, the interconnected web of all existence of which we're a part? Could galaxies then develop some form of consciousness that we can't imagine any more than the neurons in our brain can conceive of our consciousness? So here's a picture which is quite famous, the Hubble ultra-deep field. The Hubble telescope pointed itself at a small about a grain of sand at arm's length, which is tiny compared with the moon. I don't think you can see this down to the left. There's a little tiny square there. And they pointed it at a distance with no stars in our galaxy, pointing out beyond the galaxy, and doing exposure of 12 days, with this huge digital camera, and got these pictures like this. Everything in that picture is a galaxy. And when you see so many in that tiny spot, you can extrapolate over the whole sphere, and you figure out that there'd be 100,000 million galaxies in the visible part of the universe. But the universe was much younger then, so who knows about that. But so finally, and it could be finally about dark energy. This is a figure that I call grabbed. On the vertical scale, you see the scale of the universe, Big Bang down at the bottom left, time going from left to right, a sort of logarithmic scale. We're in the present time here. And you see a potential graph of how dark energy must have changed through the lifetime of the universe from the Big Bang. Now we're in the middle here, and we see that the universe is expanding faster and faster, exponentially fast. And if dark energy is constant, it's going up. But in those cases, if it's growing forever and ever, then that would mean there's infinite time, infinite future. So I said before, I don't believe that anything in the physical world can be infinite. So in my idea, dark energy must become slowing down and constant. It's not going forever and ever. Another possibility is this big crunch, where the universe comes down into the far future, where it becomes as small as the Big Bang was. But that's not considered now likely to happen. But so you can go to sleep for this slide if you want, because it's got equations on. Everybody knows E is mc squared, right? The energy of a particle is a mass times the speed of light squared. And that, of course, gives nuclear energy and nuclear bombs and so on, and powers the sun. But really, the full equation is E squared is P squared C squared plus M squared C to the fourth. P is the momentum of a particle, which is mass times velocity. So if M squared was negative instead of positive, which is a strange thing to think about, but then the energy is less than momentum. Speed is more than the speed of light. Particles always go past the speed of light. Hypothetically, it's tachyon. Tachy means fast in Greek. If you had zero energy, you'd have infinite speed, but not quite zero energy means extremely high speeds. It's sought in experiments. There are no signs of this particle. If it is a particle, which means it's very, very light or very, very weakly interacting. This little graph shows schematically energy is on a vertical scale, speed is to the right. So on the left, you see normal matter particles. You give them more energy, they grow in speed, they get closer and closer to the speed of light, which is that vertical line, m squared of 0, but they never quite get up to the speed of light. You can add more energy to electrons and give them 0.99999 the speed of light, but they never quite get there. But tachyons, on the other hand, when you give them, when they go faster, less energy makes them faster and faster, the speed goes up. So that's how that would work. So now let's think big. With 100,000 million galaxies in the visible universe, if each had some form of consciousness and dark, invisible energy rather connects them, is a tachyonic type field, then the universe also has some form of consciousness which is completely alien to us. We can't imagine it any more than a neuron can imagine our consciousness. But why stop there? If our universe is only one of a vast number, then, and I can say something about that, maybe 10 to the 100 other universes out there with all different particles, different forces. Most of them would be sterile. If the probability of life is 10 to the minus 90, which is 0.90 zeros and then 1, you still have 10,000 million universes with life, different universes with life. So is our universe unique? You know, we used to think the Earth, this was the world, that was it. And then we found other worlds out there. And then we've found galaxies out there. We've come to the universe. Maybe our universe is not the only one. This idea is called the multiverse. There are various versions of it. Some physicists say it's not science because you can't falsify it if these other universes are not accessible to us by physical means. But if this is the only universe, then how could all those physics miracles I told you about have come about? How can it be that the up quark is just a bit lighter than the down quark, enable protons to exist and so on? Those miracles of physics I talked about. Now, if there's a vast number of different universes and all have different physics, maybe they all have the same fundamental speed of light and gravity and so on, but different particles, forces, then vast number, so many maybe sterile, but you still have many that could have life in it. There's one other concept of a multiverse without any infinities where you have two radii here. One is around the ring, which is one dimension of space, but there's really three. And the other around the ring is time, which is a closed loop in this case. And universes, by the gazillions of universes, are filling up this space without any infinities in there. So that would be a sort of model of totality. So, of course, physicists are divided on this issue. Some say it's theology. Okay, that's part of my theology. Many argue that science should restrict itself to what can be known. Others say it's a legitimate area for study, even if it's always theoretical. I've got a quote here, which I like from an article in the Scientific American. As skeptical as I am, I think the contemplation of the multiverse is an excellent opportunity to reflect on the nature of science, on the ultimate nature of existence. Why are we here? In looking at this concept, we need an open mind, though not too open. It's a delicate path to thread. Parallel universes may or may not exist. The case is unproved. We're going to live without uncertainty. Nothing's wrong with scientifically based philosophical speculation, which is what multiverse proposals are. But we should name it for what it is. I said there are dissenting voices. In my opinion, either the multiverse exists with all its different physics, and we happen to be in one of the very rare cases where the physics is just right, the miracles are right to allow us to be here alive, or the physics miracles needed some sort of a design that some say God designed it so that the protons are stable and neutrons decay and so on, but you choose that. That's your choice of theology. So takeaway, and I like to have 3 things, but I couldn't help getting more. There are more things in heaven and earth, Horatio, than I dreamt of in your philosophy. That's in Hamlet, of course, you know that. We have a good understanding of only about 5% of the stuff in the universe. That's matter from tiny particles to the vast universe. And we're learning so much about that with modern science. But the matter we know, speed of light in a vacuum is an unapproachable limit. You can't get there. But these machines like the Large Hadron Collider at CERN, where I'm working, or LEP also at CERN, colliding electrons and protons, they get to 0.999999 speed of light, but you give them more energy, they get a bit faster, they'll never get up to the speed of light. The speed of light would have infinite energy on a particle, and infinity is forbidden. by my hypothesis. So these hypothetical particles called tachyons, think of them as waves, always travel faster than light. Speculation is that there are 3 tachyon fields, one at the beginning of the universe called inflation, when it went from the size of this Planck scale bit of space-time up to the size of an orange or something like that. When it stopped expanding exponentially, it got heated up, symmetries were broken, and the whole universe came from a thing that size. Okay, and so the first tachyon field was in inflation, they called it the inflaton. And then far out speculation is intermediate scale now, tachyon waves are extended and coupled not to individual electrons and protons and quarks, but to complexity. I don't know how that would happen, but it's conceivable that the particles we know and studied couple very simply to each other, but maybe this intermediate invisible energy waves coupled to complexity. Very far out speculation is an interconnected galactic web, even forming some sort of higher consciousness, which is where I can put God, like we sometimes in Unitarian say, God is the universe, God is life, God is love, and those things all come into this sort of idea I have here. But don't stop at the galaxy, the whole universe. Don't stop at the universe, multiverse, totality, think big. Maybe that is an idea to think about, and because I'm no longer paid to be a particle physicist, I can talk about these things without fear of losing my job. So I now invite you for questions. Oh, this is a great picture that was used for a particle physics priority panel, and I used it for the front of my book here, which is 100 short stories about the universe, which I've got some copies out there if you want them for $20, $19.95, but you can keep the change. And so there, I would invite questions, and have I run out of time already? Not quite, but 10 minutes for questions. But before I finish, next Science Sunday, June 8th, I don't yet have a speaker, so volunteer yourself or somebody else, volunteer somebody else. So now I will invite questions, and I'm sorry I wasn't looking at you. Caroline, you have to use a microphone.
So this is related, I think, to your first far-out speculation. Sounds like you are suggesting tachyons might be consciousness of the universe. Sounds like you might be saying or suggesting tachyons are consciousness of the universe.
I'm not equating tachyons with consciousness, but I'm suggesting that this tachyonic field, if it exists as a field, well, we know dark energy exists, and I'm saying if that is a field, tachyonic fast speed of light, it couples to complexity. I would say it is consciousness, but it allows some sort of consciousness to be coupled.
So this is always a question that I've wondered about in terms of consciousness of humans, animals. When we die, where does it go? Do you have a speculation on the connection between the tachyons and human consciousness?
Well, I thought about far-out speculations, even more far out, but I think I've come to think more and more that there's things going on, that things are happening for a reason. I don't know if, but when I die, first I know that you live on in the things that you've done, the changes you've made. If you've got children and grandchildren, you live on in that sense. But maybe you also do live on in some sense. I'm talking about what people might call a soul, and Sterling's shaking his head, right? But it's conceivable to me that even though I believe when I die I don't have memories or feelings, I can have feelings, emotions could continue into after I die. So of course, I don't know about that. A lot of religious people say, yes, your soul escapes and goes to heaven and merges with the great soul in the sky, which could be invisible energy. But so I'm not Paul Grundy, he's what's the term you use for you and me?
A dualist. A dualist is somebody who thinks there's something other than the material world, something other than those things that obey the laws of science and nature. There's something out there that's spiritual, that's, that's my question. In your view of dark matter, would you think of that as being a dualist? I mean, is that some sort of spiritual energy, some sort of something that doesn't follow the standard laws of nature?
Yeah, I have become a dualist, I think. That, there are two qualia, if you like. There's the world of matter. We understand that in physics, we can study that. Chemistry and biology is the world of matter. But on the other hand, there's a parallel world, I believe, which is about to do with consciousness and feelings and the whole universe. And this invisible energy could be, so it could be something to do with that. So it could be that our souls, if you like, which Sterling will object to, merges with this invisible energy. And it's even possible, when I think about it, that this dark energy or invisible energy came into existence with the beginning of complexity in the universe. And it's grown, and now it's maximum. But it's going to disappear. It can't go on forever. By hypothesis, the universe cannot go on forever. So it's going to die away. And it could die away when complexity has died away. Now, many physicists think that even protons, which seem to be stable, we know they live for at least 10 to 30 years, but they will die away. Grand unified theories, which unite the theories, the forces, say that in about something more than 10 to the 30 years, protons will decay away. A proton becomes a positron and a photons. And so the universe will then be only electrons and positrons and photons. Now, a very simple universe. And then if complexity has died away, perhaps this invisible energy has also, or dark energy has also died away. So it's not going to go on continually expanding forever. And then in the far future, more than 10 to the 40 years, maybe all black holes have to decay away as well, which will take longer because the black holes radiating, but they have to be warmer than the space around them, which means that the universe has to cool enough for black holes to evaporate away. So that could be 10 to the 100 years, whatever. But in that time, the universe has become very simple. And in my topology, at the very beginning, the universe and anti-universe split. There's an anti-universe, which is parallel to our universe, where all the antimatter is. And in the very far future, it comes back together again, because both our universe and the universe of antimatter will both become simple again with just electrons, positrons, and photons, and their states will be identical. And that closes a time loop. So time is a closed loop in this model for electrons, positrons, and particles. But the time, but the time of our lives is not a closed loop. The time, our psychological time, entropic time, only started when complexity came into the universe, symmetries were broken, and it will disappear again after the last complexity decays away, which is after protons decayed. So they have two distinct times. A time of particles, where if you, Feynman said, at that space, time is reversible. We find in particle physics, for electromagnetism, time is reversible. You can't tell the difference forward and backward until the weak interaction comes into existence, which is not right at the very beginning. And that broke symmetries. And the weak interaction does violate time reversal symmetry. You can tell if a movie is going forward or backward with a weak interaction. But that only came into existence, I believe, not right at the very beginning, but during the inflation period. And that brought complexity and broken symmetries into the universe. And eventually, obviously, psychological time will disappear when all life has gone away. But entropic time will disappear when all complexity has gone away. So this is obvious. Anyway, sorry, Sterling's disagreeing with everything I say. He's boring.
I just wanted to say, to me, a dualist is somebody who believes in the natural world and the supernatural world. But I'd like to, and this is such an amazing sort of lecture presentation that you've made. It's just amazing. But I'd like to get down to something very practical, and that is a friend of mine 25 years ago who was an electrical engineer said that if I knew that there is energy in my backyard and I can tap into that electrical energy in my backyard, your slides seem to support his theory. You were talking about the amount of joules that were in 1 cubic meter of my backyard, 6 times 10 times 10 to the 10th or 100th power of joules of energy. So I'd like to know how you and I are going to get the right conductors and electrodes down into my backyard and tap into my electrical energy, which will be free. We can't do it at your place because you don't have a backyard, but I do have a backyard.
Well, if you figure out how to tap into dark energy, I say it's so diluted. In a cubic kilometer, you've got enough energy there to light a bulb up for a minute or so. That's in a cubic kilometer. How do you tap into that? I don't believe you can. The Higgs is another field that fills the universe, and that we don't know how to tap into that. Well, we do in a sense when I'm just thinking on the feet. But when you get energy from atomic reactor, for example, you're actually changing quarks from up quarks to down quarks or the other way around, and that is generating energy. And the quark masses come from a Higgs field. So it's a thought, maybe we're extracting energy from the Higgs field. So, no. Anyway, I'm sorry, this is being recorded. Stop the recording, stop the recording. Bob.
I can't resist suggesting this science fiction theme, which is if consciousness is connected to tachyons in some way, and the tachyons move across the universe or vast distances very quickly, it might be that if such a thing is caused, if there is a religious experience and consciousness affects, connects with us in the real world, then what we might have is a form of communication through consciousness that connects the universe. So by, let's say, meditation, one might be able to tune into the life and the rest of the universe. I'm saying that it just seems like fruitful ground for science fiction and a whole other way of seeing things. But it has obvious challenges too. So in any case, I thought I'd share it.
Yeah, you're right, and this is part of my science fiction story. So imagine, there's something. Think of a Hitler rally where he got thousands of people to hate, and were they just, in the crowds, were they just seeing and hearing him and maybe some smells are around, or was there something in addition, some extrasensory thing that's transmitting feelings? And then you have a love fest, a religious revival where people are all feeling the love, and maybe this is something to do with this individual energy field that can transmit feelings, but not, I would think, information. Not information, but feelings.
There are measurable brain functions that synchronize when you're in a group. So people are very sensitive to one another when they're together. And this is another dimension of that.
Yeah, I've written a short science fiction story called In the Tank, where a physicist and a psychologist get together to do experiments about extrasensory. So they have these two people in separated tanks, no possible physical communication between them, that actors actually, and in the dark, one sees the word love coming up briefly, and he feels love as much as he can, and the other person in the other tank has to say, if they one of four, love, hate, joy, or pain or something, and so they do this experiment to try. So telepathy, card guessing doesn't seem to work very well, although some people claim it works a little bit, but I don't believe it does. But transmission of feelings through a sixth sense, if you like, is not inconceivable to me that you have this, and that's where. So yeah. Anyway, but we all can build our own theosophy, hey Bob?
Mike, I'm sorry I came in a little bit late. Maybe you already touched on this, but I'm extremely interested in where this work is done, and all the particle physics work is done at CERN in Switzerland, which you would, of course. But the future is going to be something really big that's going to be happening there, I understand from someone just recently. Can you say a word or two briefly about what's ahead at CERN?
Yeah, well, we don't know exactly. I mean, the first colliding beams of protons on protons was when I was just a postdoc at CERN, called intersecting storage rings. And then it went bigger and bigger and bigger. Now the Large Hadron Collider, where I'm still working for fun, is 16 miles around underground, full of superconducting magnets. And send protons in both directions colliding at 4 places around there with huge experiments. I showed you one, huge detectors. And there's 3,000 to 4,000 physicists in each one of these projects from all over the world. And I talk about physics as a force for peace in the world. And that was true until Russia invaded Ukraine, but whatever. So the next, CERN wants to go next step. The Large Hadron Collider is planned to run till about 2040, 2045, something like that. But then they think the future, they have to have a future, which is a bigger machine. They talk about one called the Future CERN Collider, which is about 90 miles around, or 90 kilometers actually, I think, under Lake Geneva and so on. And they want to start putting a ring with electrons colliding with positrons to study the Higgs and other things in great detail, and then put in protons colliding with protons. And I call it omnitron for everybody, but I don't, anyway. The CERN obviously wants to have a future. Now, I have some skepticism about that, because it could be that it doesn't give us access to particles we haven't yet discovered. Okay, it could be, because the dark matter we think is made of particles we haven't found yet, but they could be 20 times higher at mass to find at this machine. So we have the standard model of particle physics. Dark matter is out there, but we don't know what those particles are. And they could interact gravitationally, because they've only been detected by astronomers seeing galaxy rotation curves and saying there's more mass in there than we know about. Only astronomers have talked about, given evidence for dark matter. Yeah, we don't know what it is. But if it only interacts gravitationally, we haven't got a hope of detecting the individual particles. We just see the effect on a big scale. But hypothetically, there could be particles that connect to dark matter and to normal matter that we know about. And they're called portals to the dark side. An experiment I'm working on is going to be looking for these portals. They can be produced in a collision, but they're very weakly interacting, and they could travel through 30 meters of iron and then come out the back and decay back to standard model particles. So that's a project that I'm still working on in my spare time. Any more questions? Yes, Caroline again?
I think you already said it. It's still not completely agreed upon that dark matter is a particle. It could just be a slight change to our theory of gravity.
Yeah, this has been considered and discussed, that maybe gravity has a different behavior on a large scale. It doesn't go like 1 distance squared and so on. And I don't know. It's not considered the prime solution, but it could be. It's not. Or, I mean, we think of all fields have particles with them, and maybe this is a field that doesn't have particles. It's just some sort of continuum. That's a really strange idea. But or it could be a whole spectrum of particles of different masses. I mean, neutrinos are part of dark matter, but there's only a very small part of it, we think. Like, there's not enough neutrinos, even coming from the Big Bang and everywhere, to be all of dark matter. So there presumably are other particles to be found, but they may be so massive we can't get them. But yeah, and modified Newtonian gravity is a possibility. I don't think it's considered a front runner, but it could be. Okay, well, thank you everybody for coming. Okay.